So let's see. If you're comfortable at least with the fact, oh, and actually there's a good little geek humor now. If you go to google.com, and suppose you're wondering what recursion is, especially a few hours from now, well, you can Google it. And then the computer scientists at Google, there we go. OK, so if you're laughing, you get it, which is great. So that then is recursion, something giving you back an answer in terms of itself. So why is this useful? Well, it turns out we can leverage this now to solve a problem if we know that we can actually convert it to code. We'll focus less on the actual implementation and more on the idea, but let's see if we can't wrap our minds around the problem to be solved with this code. This is merge sort in pseudocode. And again, like all the pseudocode we've ever written, you could write this in bunches of different ways. Here's one such way. Notice the first thing on the input of n elements, so n numbers, n blue books, and whatever, go ahead and do the following. If n is less than 2, return. So it's a little different from the condition I had a moment ago, but the context here is sorting. It's not summing. So why is it logically OK to say if n is less than 2, just return? Yeah, that's just itself. If it's less than 2, that means there's only one blue book, or maybe even 0. So in either case, there's no work to be done. Just return. The list is sorted, however short it is. But if it's longer than that, you might have to do some work and actually do some actual sorting. So what happens then? So else, you know what? Sort the left half of the elements, and then sort the right half of the elements, and then, OK, merge them together. So it's this same kind of like blasé attitude where, like if you ask me to sort something, I'm just going to tell you, well, you go sort the left, then you go sort the right, and then we'll just merge the results back together. And this is cyclical in the sense that how do you sort the left half of anything? You need a sorting algorithm. But this is the sorting algorithm. So this is like saying use merge sort to sort the left half, use merge sort to sort the right half, and then merge them together. Merging doesn't really need to be a fancy algorithm. Merging is like if you've got one pile of numbers here that are sorted, one pile of numbers here that's sorted, you can just kind of eyeball them and grab the appropriate one to kind of interleave them in the right order. That's what we mean by merging. So how in the world is this even correct? Because we haven't actually done any apparent work in this way. There's no loops. There's no comparisons, it seems. It's just completely recursively defined, so to speak. Well, let's see what actually this means. And this is a sequence of visualizations that can you can potentially fall off the story of. So I'll try to go slowly, but not so slowly that the example itself is boring. We'll just go through this once, and then again, the slides are online if you kind of want to step through the visualization. So here is a list of 8 numbers, the same 8 numbers that we looked at before. I've drawn them contiguously as though they are in an array. This list is currently of size 8. So an input of 8 elements is the beginning of this story. What was the first step in our algorithm? Well, we were going to check if n is less than 2, return. That is irrelevant because n is 8, not less than 2. So that's a moot point. So the first 3 things for me to do to sort this list is to sort the left half, then sort the right half, then to merge the sorted halves. OK, so let's see how we get there. So here's the list. Here is the left half. And I need to sort the left half, apparently. How do I do that? Well, how do you sort a list of 4 elements? Break it up again. Sort the left half, then its right half, then merge those 2 halves together. So let me do that. I'm going to draw a box around only the elements we're thinking about at the moment. So let me look at the left half. OK, now I need to sort this list. How do I sort a list of size 2? It's actually 2. It's not less than 2, so I have to do some work. So how do you sort a list of size 2? It's a little strange to say it, but sort the left half, then sort the right half, then merge the 2. And at this point in the story, you may very well be lost because we literally just keep saying the same thing and not actually doing any work. But think of it like you're buffering these instructions. Like I've said to sort the left half, then the right half, but you focused on just the left half for now. But unfortunately, you got a little distracted because now to sort the left half, you have to sort the left half, so you have to do a little more work. So if you just kind of let this mental baggage build up, we have to remember to go back through it. But we've not actually done the real work yet. We're about to now. Because now that you've told me, given a list of size 2, sort the left half, here's where we bottom out with that base case and actually start to make some progress. So here's 4 and 2, a list of size 2. Let's sort the left half. How do you sort a list of size 1? You don't, right? Because n is 1. 1, of course, is less than 2. And what was the one instruction we had at the top of this function merge sort? Just return, like do nothing. So OK, everyone, I have now sorted the number 4 for you. Like, it's true, it's kind of a foolish statement, but the magic must therefore come when we combine the results. So let's see where the story goes. I've sorted the left half. Done. Return. Now, what was I supposed to do next? Now I have to sort the right half of that list of size 2. OK, done. What's the third step at this point in the story? Merge them. So I'm now looking at a list of size 2 again, each of whose halves is sorted, according to the crazy logic we're using here. But now something interesting happens. I have on the left the number 4. I have on the right the number 2. And each of these lists is of size 1. And if you vary in your mind's eye or just visually with my fingers, consider like your left hand pointing at the first list, your right hand pointing at the second list. The process of merging numbers is just comparing what your fingers are pointing at and deciding which one comes first. Obviously, 2 is going to come first. So in a moment, we'll see that 2 should move over here. And then there's nothing left for my right hand. It's done. So 4 is obviously going to go here. And that process of merging 2 followed by 4 is what we mean by merging. It's pretty much what I was doing with insertion sort, but here we're just doing it with individual elements at a time, kind of weaving things together or zipping things together with like a zipper, if you think of it that way. So now let me grab 2 and put it here. Let me grab 4 and put it here. OK, so I sorted left half. I sorted right half. I merged them. How do we unwind the story? Where did we leave off? Now we have to sort the right half that was like a minute ago in the story, which, just to highlight it now, is the 7 and 5. So now I have to do the same thing. I'm sorting a list of size 2 that happens to be on the right of the left. So now I sort the left half. Done. Sort the right half. Done. I now have to merge the 2 together. So now my hands have to do some work, but I'll just do it from over here. 5 goes down. Then 7 goes down. And at this point in the story, we have sorted the left half of the left half and the right half of the left half. So what point in the story are we at now? All right, we did the right half just now. We now have to merge the 2 halves together. And frankly, if you do this at home, if you want to kind of retrace your steps, literally just write down a to-do list, like from top to bottom on the sheet of paper. And then as you do something, cross it off and go back to the previous thing in the list. You would actually see or feel even more what it was, that mental baggage you were accumulating that you need to tend to. But now I have 2 lists of size 2. So let's do the finger thing again here. So I start pointing at the left list, start pointing at the right list. The first number to merge in is presumably going to be 2. Then what comes after that? I'm going to update my left finger. So now my left hand's pointing at the 4 at this point. My right hand's still pointing at the 5. So which comes next? 4. There's no more work for my left hand, so it's probably going to be pretty trivial, 5 and 7. But I do need to do the merging. It looks merged already, but we have to do it. And I'm going to do it in some new space just as before. So 2 and 4 and 5 and 7. And now you can really see it for the first time. The left half of the original list is finally sorted. Unfortunately, like 3 minutes ago is when we started this story, and now we need to unwind in our mind to go back to the original right half. So if you think about it now, even though I've said a lot of words, this is technically the second step in our algorithm, or at least the first invocation thereof. All right, so we'll do it a little faster, but same idea. Sort the left half. How do I do that? Sort the left half, then the right half, which are stupidly easy and done, but now I have to merge 6 and 8. So merging in this case didn't have much effect, but it needed to be done to be sure. Next, let's sort the right half of the right half. Now I'm going to sort the left, sort the right. Now the key step is merging, and now we're doing some actual work, and now we really have some work to be done. Now we have to sort the left half and the right half of the original right half. So it's 1, then 3, then 6, then 8. Now we're finally almost at the end. Now what do we do with these? Now we have 2 halves, the original left and the original right, and you can think of the fingers as doing the work again. 1's going to go here, 2's going to go here. 3's going to go here, then 4, and I constantly compare where my fingers are pointing, but my fingers are constantly moving from left to right. As soon as I deal with a number, it advances to the next number in the list. So it's obviously going to be now 1, 2, 3, 4, 5, 6. But notice, if you imagine my fingers doing this work, they're constantly moving toward the right to the end of the list. So as soon as my fingers hit the ends of those lists, I must be done merging. And voila, we've now sorted the elements. It's a huge number of words, and it would be a nightmare to kind of do it with humans because there's just so much going on, and you have to remember or buffer so many of those steps. But in the end, we've done something that is kind of captured even by this picture. So it turns out that merge sort, even though it sounds like a long story, is fundamentally faster. And it's fundamentally faster because we're dividing the problem in half as we have been doing with binary search in the phone book example even days ago. So if we look on the screen, you can kind of see the sort of the remnants of work that we've done. Like how many times did we move the elements from one row to another? They started up here, then they eventually made their way here, and then here, and then here. So that's 1, 2, 3 movements of the letters, or of the numbers in memory, if you will. So if you imagine each of these rows is just a different chunk of memory and RAM, I'm just moving things around in memory. So 3 is just a number, but it turns out, and if we did more general cases of this, turns out that log base 2 of n, where n is 8 is the number of elements we started with, log base 2 of 8 is 3. And so indeed, and if you'll take on faith for now so that we don't have to go through an even bigger example to show it even more, the number of times we move the numbers is going to equal, it turns out, log base 2 of n, which in this case happens to be 3. And so that then invites the question, on each of the rows, every time you move these numbers into a new location in memory, how many times are you touching that number while it's in that position? Or how many times equivalently are you looking at it to do something about it? What do I mean by this? Well, the movement from top to bottom was happening anytime we did the merging, right? We would move the numbers from here to here, but as soon as we did that, we had to do some work with the left pointer and right pointer. I needed to then merge those together. And I emphasized earlier that anytime I'm comparing numbers, my left hand and right hand are constantly advancing from left and right. I never double back, much like I constantly was doubling back with bubble sort, insertion sort, selection sort. There was so much damn comparison going on. It felt like a lot of work, and it physically was. But here, merging, I'm moving things around, but my hands are constantly moving forward, looking at, on each row, n numbers total. My left hand or right hand pointed at each of the numbers once. Never doubled back. So it was never n plus 1 or 2n. It was just n. So we have log n movements of the numbers in memory. And every time we do that, we merge them from left to right effectively, touching each number once. So we're doing n things log n times. And so that would be mathematically equal to n log n. So again, even if you're not super comfy with logarithms, you do know from our picture with the straight lines and the curved line that which is smaller, log of n or n, generally speaking? Like log of n is smaller, right? That's why the green line was lower, and it was also curved. It was below the linear line n. So generally speaking, the bigger n gets, the more slowly log n grows. And again, if just take on faith that this is a mathematical expression that communicates the time required to do something, it's less. So which therefore is smaller? N squared, which of course is n times n, or n log n? N log n. So we've now found an algorithm that's unlike all of the others we've seen. And even though it took a while to explain, and even though, frankly, you might have to kind of sift through it again to really wrap your mind around it, it took me a while too, it is fundamentally faster as well. So just to take one other stab at this, let me show one other perspective, at least if you're more mathematically comfortable. And after today, if you're worried that this is way more math than you were expecting, realize we very quickly abstract away from these details and we start to wave our hands using big O and big omega. Let's consider how we could look at this a different way. If the picture wasn't really working for you, let's see if we can just jot down how many steps each of these lines of code is. And there's not many lines of code here, so it shouldn't be a very long expression. So how long does it take to decide if n is less than 2? And if so, return. Well, you're past a bunch of numbers, so I'm going to call it constant time. Like you know how many numbers you've been handed. Nope, it's not less than 2, or yes, it is. You're just answering yes or no. Constant time, big O of 1. All right, so I'm going to describe that as this. This is the formal way of saying it. T of n, which is just how much time does it take given a problem of size n. Just a fancy way of saying that. It's on the order of 1 step. Maybe it's 2, maybe it's 3, because you kind of got to look at something. But it's a fixed number of steps to decide there are fewer than n elements in front of me. It's not going to take you very long. So that piece of the puzzle takes big O of 1 step. So now we have 3 other questions to ask. That's like kind of a throwaway. That's really quick if it's just 1 step or 2 steps or 3 steps. So are these the expensive things? Well, let's see. Sort the left half of elements. Well, here too I can be kind of clever and propose the following. You know what? The amount of time required to sort n elements is technically equal to the amount of time it takes to sort half of those elements, plus the amount of time required to sort the other half of those elements, plus, to be fair, some merging time. And it's essentially n, but I'm going to generalize it as big O of n because I did have to move my hands around. But again, the key thing was my hands were constantly moving to the right. There was no looping back and again like with the other algorithms. So it's like n steps to do the merging. If I've got 4 numbers here, 4 numbers here, I have to touch a total of 8 elements. 8 is n, so it feels like, yes, on the order of n steps to do the merging. Unfortunately, this is like a recursive answer to the question of how efficient is merge sort. But that's kind of consistent with the fact that merge sort is being implemented recursively in this code. And it turns out here too, if you've got one of those old school textbooks that's got a cheat sheet in the front or the back of your physics or your math book, this is a series that you can actually, that mathematicians know, actually sum up to something known, which is n times log n. And we won't go into the weeds of why that is mathematically, but if you take a problem of size n, and add the running time for first half, second half, and then add in n, this is what mathematically it ends up being. And so if you're more comfortable with that, realize that this derives from just counting up of those several steps. And ultimately, this is much better